Thank you, Matthias, for pointing out that the title is slightly different from the one that's published. In essence, it's a greedy approach, so we are not wrong in having this title as well. This is joint work at the School of Information Systems in the Singapore Management University with my faculty colleague, Pradeep Varakantham, whom some of you may know. Regrettably, he's unable to make it to the conference. And Pallavi Manohar, who was a postdoc hired to work on this project. This project is basically with a emergency response agency of a large Asian city, whose name I will not mention. And some of this data that they give to us, they tell us to masquerade it, so the experimental results, which I'll present later, will also have some delta and epsilon in it so as to masquerade the actual numbers. Okay, what I'm going to do is to provide some motivation and talk about a solution approach and then give you some experimental results. The motivation is really that of providing effective emergency response. Every minute, a life could be lost if the ambulance or the fire engine doesn't arrive on site. So the model that we are working on is really that when an incident occurs, let me try this out. Oops, no, wrong one. Oh, wrong button, sorry. When an incident occurs, there will be some emergency response vehicle, ERV, which I will use ambulance synonymously. Typically, the nearest one that is available will be dispatched. And this vehicle will travel, and the travel time is really the key concern here. We call it the response time, the time to move from its base to the incident site within a certain number of minutes. And then it will fetch this patient to typically a hospital, and then this vehicle will then be cleared and returned to base to be ready to serve the next incident that arises. So when we are dealing with this kind of problems, typically there are several kinds of concerns ranging from the strategic level to the tactical and the operational. At the strategic level, people will be asking, how much do we invest in the fleet size? Do we need 60 ambulances, 80 ambulances to cover the city? Where should we locate the base stations? Would it be near to some estates where incidents are more likely to occur, or what? So that is one line of work. Another line of work deals with the tactical concern, and that is, given that we have the fleet size, let's say 100 ambulances, given that we have the locations at of the bases in various places in the city, which location should have how many ambulances of what sorts? Okay, so and that is the concern of this paper, and we make a simplifying assumption that all ambulances are homogeneous in this paper. And then finally, in the operational context, when an incident occurs, how do I know which ambulance should I dispatch? Is it necessarily the nearest one? Usually, we will do that. It's just common sense to do that. But it's not necessarily the optimal. If you think of it over a rolling horizon, perhaps that ambulance could better be served to be reserved to serve higher priority incident that will occur in the next minute or so. And that line of work was actually taken by a colleague, a research engineer of ours working on this project in the morning session in that paper in ICAPS. So let us very quickly say that for this kind of problem, the important characteristic is that incidents are very uncertain. They arrive over a certain spatial-temporal distribution, over space, over time, and these incidents occur in real time. That means we are not going to say, I have this model, I have this input, and then I produce the allocation. No, the allocation has to be produced a priori, such that it has to deal with incidents that arise in real time, and it should still work. Okay? So and we also assume that certain dispatch policy is given. Typically, such dispatch policy is fixed. It could be the nearest neighbor, like I mentioned just now. So what do we have? We will be given a historical log of such incidents. Okay, maybe for the past 1 year, we know which location, what time, what incident has occurred, and what sort of condition of the patient, for example, to give it a sense of priority. And then we're also given the list of base station and the fleet of ambulances. Given that, what we do is to try to generate a location for each ambulance. Okay? Subject to one or more of such criteria. The first one is bounded time. This was a common kind of objective where you are given a bounded response time, let's say 10 minutes. Okay? Within this 10 minutes, I want to maximize the percentage of incidents that can meet this response time. In other words, the ambulance will arrive at the scene within 10 minutes from the time the call is made. Okay? So that is what we call a bounded time criteria. And this morning's session talk has this flavor of bounded time for various incident priorities. And then there is another kind of objective function, which is what we did a couple of years ago at AAAI, and this was bounded risk. We flip it the other way around. We say that if I want a certain percentile of incidents to meet that response time, let's say 90% of the incidents, what is the least response time that I would be able to have? Okay? So that is the work. Okay? Moving on. So what have people done, right? So typically in 3 areas. At the operational level, like I said, there is the dispatch policy type of work. And these papers are taken from the OR literature, typically. And they deal with generating dispatch policy, which may be nearest neighbor or some other more clever dispatch policy. But we question the kind of the efficacy of this kind of work because in a real context, such kind of smart dispatch policy may not be really operationalizable given the situation on the ground with so much dynamism and so much uncertainty. Whether such smart policy would beat the nearest neighbor policy, we do not know. Okay. Moving closer to the planning kind of realm, we have this reallocation type of work, meaning that the ambulances are already at their respective bases, it's been planned for. Periodically, we may need to reallocate such ambulances in order to better fit the spatial temporal pattern of arrival of incidents. So again, we have drawn from literature from some OR literature, and there is some work that uses MDP as a model and approximate dynamic programming to solve this MDP model to generate or to find such optimal reallocation strategies. Such kind of work are also very fun and interesting. However, again, in the literature that we have found so far, they are usually concerned with a small selection or small number of such vehicles because the MDP basically doesn't scale up very well. So in the Maxwell paper, if I'm not wrong, the experimental result shows that the number of ambulances they deal with is about 24, 25. We are dealing with 100. So that is the kind of gap that we find. And then there's also another line of work that deals with heuristic planning but without performance guarantee. Then come closer to our world. We are interested in data-driven allocation, and also I put in bracket reallocation because if you specify the time interval small enough, basically this can be turned into a reallocation strategy. We have seen work coming out of AAAI in 2012, and we have also some work in AAAI 2015, and the idea is to build on such data-driven approach and by providing a better greedy algorithm. So that is the essence of this paper. So the contribution of this work includes the following. We look at the arrival pattern, and we develop a Poisson Point Process to model the arrival pattern of incidents. And we define what we call the bounded rank objective. And this is in opposed to the bounded time objective, which I told you about, where you're given a response time and you have to meet that response time. Now, the bounded rank objective is a sort of a relaxed version or a proxy for bounded time, and it is much easier to compute. It is simply this. If I give you a parameter k, let's say k is 1 or 2, then whenever an incident occurs, I will say, can I serve that incident using 1 of the nearest base station, if k is equal to 1, which is the nearest station, if not the next nearest station where an ambulance is available. Okay? Now, so if you set k sufficiently small, and you can guarantee, let's say on your map, that for every such, for given value of k, the travel time from the base station, the k nearest base station to any incident would always be less than a given response time, then you actually meet the response time target as well. So it is an indirect way of dealing with bounded time. But the advantage of having this bounded rank is that it is easy to compute, like I say. And the greedy algorithm actually gives a very nice property, which I'll explain a little bit later. So, in fact, yeah, the second contribution will be given this bounded rank objective. We show that it is monotone submodular. And given that, the greedy algorithm picks the ambulance, the ambulance to assign to every, to pick the base to be assigned to every ambulance in a greedy fashion, okay, based on some marginal utility, which I'll explain in a minute, will always provide 50% optimality. Okay? And lastly, this is the experimental portion. We apply our strategy on two real-world set of data from two different cities, and we find that by optimizing on the bounded rank, it actually provides better results. Now, so some background. Some of you may know this work if you are in the OR community. First of all, submodular function. Okay, a submodular function is defined based on a set. Okay, and it basically says that the marginal gain you get from adding an element to the set is non-increasing as the size of the set. So an example is that this lunch, you had a lot of food, right, that's served on the table. The marginal utility or the marginal gain that you have from consuming a piece of sushi will be dependent on how much food you already have in your tummy. The more you have in your tummy, the less the gain or the utility you derive from eating that piece of sushi. So that is a submodular property. Okay? And right now, basically, you are in a submodular situation also because as time elapses, your attention span is getting less and less. So the marginal utility you gain from attending such an interesting talk that I give will be less because you have already attended a lot of such similar talk throughout the whole conference. I agree. So that's basically a concept of marginal returns that we see in the real world. Okay? Now, it turns out that maximizing a submodular function is an NP-hard problem in general. However, the good news is that if the function is monotone, in other words, the utility, okay, of a set, okay, is actually always monotonically increasing with the content you put into the set, the elements in the set. Then we have an interesting property from a very old result based on Hauser, Woozy, and Fisher, that the greedy algorithm always produces a bound, which is 1 minus 1 over e, which translates to about 63% for such a problem. And the greedy algorithm basically works in a very simple way, right? It picks an item and it gives it to, in our case, it picks the base, okay, associated with the ambulance, and in a way that will always maximize on the marginal utility, okay? In the interest of time, I will have to skip a lot. Now, on top of that, if we have a matroid, which defines a set of feasible solutions, then the greedy algorithm is a little bit weaker. It always gives you a half approximation result. Okay? So what we do now is that we basically take our problem, we map it to a Poisson Point Process, okay? And we define the bounded rank function as follows. The most difficult part of this work is really the definition of this probability, okay? That an incident occurring at a particular location will be served by a rank less than some given k. Okay? And we calculate it using this formula here. Basically, in the interest of time, I will not explain. It is basically explained in the paper. So given that we have that function defined, basically we proved in the paper that it is monotone submodular, and hence, using the result of Fisher and Hauser-Woosley, we are able to achieve a 50% optimality in the worst case. Now, it turns out that in general, this bound is actually quite loose. Okay? We are able to tighten it by saying that the gap between the optimal solution, okay, and what we obtain is bounded by this much here. Now, what is this? The value of m is really the number of changes between the optimal solution and our solution. So if we have a solution which is not very different from the optimal solution, okay, let's say out of 10 ambulances, only 2 are different, then the value of m is 2. Okay? So if you take that, then this second term in the expression basically is how many percentage of the incidents are actually different from the optimal. Okay, so if m is sufficiently small, which it is typically in the real world because ambulances are homogeneous, something like 10%, then we have actually achieved a 90% optimality result. Okay, so with the remaining 3 minutes, I'm just going to say that experimentally, we have taken this greedy approach. We have a baseline, compared with the baseline, and as well as compared with the bounded time. And we use a simulator to simulate events, basically, that we learn from, or we derive from historical records. Okay, and this simulation is actually done in a very straightforward fashion. Incident would occur, and the ambulance that is nearest to it will be dispatched, and then it will not be available until it goes to the hospital. And so at the end, we are able to compute all these metrics in terms of its amount of incidents that meet the response time. Okay? With that, we experiment on 2 different data sets. The first is a data set from an agency of a large Asian city. So the experimental results we see on paper is a bit cryptic. Let me just quickly tell you. Basically, these are the 3 approaches in the row here. And what we have done is really to measure the percentage improvement over the baseline for different values of the response time. This value could have been given in black and white, but it didn't because we were barred from actually using actual numbers. And even the number of ambulances that we use, we are using some value of B minus 9, B, and B plus 11, whatever B is, okay? So trust us that we actually use the real test instances, and we have actually gotten improvement of results. More specifically, if you look at this bounded rank one, it actually achieved a higher percentage of improvement over the bounded time one. Now, you may think that 1% is just trivial, but 1% of a 600 to 700 incidents per day for that Asian city translates to 6 more incidents that can be served by the ambulance within the response time. So that is actually quite an achievement. Now, in terms of timing, also that we managed to save a fraction of a minute, which is like 20 or 30 seconds using our approach. Again, every second counts, so if you can save 30 seconds of response time, you actually have done quite a lot in improving the quality of the allocation. Now, I'm down to 1 minute, so the second one I will just skip, and I'll just go and say that this is what we have done. And in the larger context, what the group is trying to do is really to combine OR with data science and machine learning for public safety and security problems. And I've given you here 2 sets of examples. One is what I've just presented on emergency response. There's another line of work on law enforcement as well. And that's all the time I have. Thank you very much.
Okay, thank you for your talk. So there's 1 minute left for a question.
Yes.
You used a historical data set to validate the performance improvement. Did you also test it against saturation attacks, events that are not very common, but that you have a lot of victims in some part of the city, where your system is constrained because there is not enough capacity?
Yes, okay, so good question. It depends on what you are measuring. In fact, the metric that we have is actually taken over a 1 month duration. So if on a particular day there is a big explosion and then you are failing in all these incidents, it actually doesn't really matter, because over the average of 1 month, you can still beat the percentile of
it's still representative, that 1% improvement is still representative in these kind of cases.
That's right, that's right. We have actually looked at historical incidents, and there were events, in fact, that occur in history where certain day there's a spike where your response time or your number of incidents met within response time was very miserable. But taken over, again, a prolonged period of time, such as 1 month, this was okay. So that was what we were interested to measure.
Yeah. Okay, thank you.
Thank you.